Welcome back. Today we're going to be looking at the third topic in our unit, and the topic is mutually exclusive events. Up to this point, we've looked at a review of probability, and we've also looked at the difference between odds and probability. And now we're going to start getting into some compound events where we're going to be dealing with ands and ors. So today we're looking at mutually exclusive events, and in the next lesson or the upcoming lesson, we're going to be looking at independent and dependent events. All right, so let's start off by talking about what is a mutually exclusive event versus non-mutually exclusive. So the example here says two events, A and B, that cannot occur at the same time are mutually exclusive. And as we work through this, we're going to use formulas and we're going to use Venn diagrams. So here I'm modeling it with a Venn diagram. So if two events cannot occur at the same time, they're mutually exclusive. That means they have absolutely nothing in common. There's no overlap, so they're disjoint. Now, if I wanted to represent this as a formula, I have the probability of A or B is the probability of A plus the probability of B. That can also be written as the probability of A or B equals P of A plus P of B. And since they never intersect, the probability of A and B would be 0. Now, as we're working through this, it might be important to have your formula sheet out because the formulas that we use here are all on your formula sheets. Now, two events A and B that are not mutually exclusive have common outcomes. In other words, if I were to draw a Venn diagram, there would be an overlap. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. In other words, the probability of A plus the probability of B minus the overlap. Now, if we want to identify a mutually or non-mutually exclusive event, we can do that one of two ways. We can use a Venn diagram or we can use a formula. So if we're using the Venn diagram, you're basically looking for overlap. So here's two scenarios. The first one says aces and kings. We're looking at this events aces and events kings versus hearts and kings. Well, aces and kings are mutually exclusive because you can't have a card that is both an ace and a king. But hearts and kings are not mutually exclusive because it is possible to have a king of hearts. And if we can have a king of hearts, that means there's an overlap, so it's not mutually exclusive. Now, if we're trying to do this mathematically, essentially what we're trying to do is we're trying to use a formula. Formula, we're going to use that probability of A or B. So if we want to use a formula, we're going to use the union formula. So we're looking to see, is the probability of A plus the probability of B equal to the probability of A or B? And so we take a look at the example here. It says if the probability of A is 0.2, the probability of B is 0.35, and the probability of A or B is 0.51, are they mutually exclusive? Well, if we add these up, 0.2 plus 0.35, we do not get 0.55 or 0.51. So these are not mutually exclusive, or we can say not ME. All right, so let's take a look at some examples. So example number 1 says to consider the experiment of rolling a die, and we're going to let event A be an even number being thrown and event B is an odd number being thrown. So if we want to write this in a Venn diagram, even numbers, we're going to have 2, 4, and 6, and odd numbers would be 1, 3, and 5. If we wanted to list these as sets, so this is going back a little bit to a previous unit that we've done, if we want to list these as sets, we would have 2, 4, 6. So essentially we're listing our sample spaces, and 1, 3, 5. Now the event A or B would be 1, 2, 3, 4, 5, and 6. And the event A and B, essentially the overlap, is an empty set because there is no overlap. You could also write it this way using empty brackets. Now, if we look at the number of elements in A, there are 3 elements in A. There are 3 elements in event B, and there are 6 elements in A or B, and 0 elements in A and B. And lastly, if we were to look at the probabilities, the probability of event A occurring is 3 out of 6, which is 1/2. The probability of event B occurring is 3 out of 6, which is 1/2. And the probability of A or B occurring is 6 out of 6, or 1. So it's a certain event. And then probability of A and B is 0 out of 6, meaning it's an impossible event. So if we look at this question here, there are no overlaps. There's no overlaps at all, so the events A and B are called mutually exclusive. And as we go forward, you'll see me use ME for mutually exclusive. Now, if there's no overlap, that means, going back to our sets unit, that means the two are disjoint. Okay, so A and B are disjoint because there's no overlap. Now, we can verify this using a formula. And so when we're doing this, we can use left side, right side. So we can draw a line down the center. Do the same over here if we're going to get to this one. And using left side, right side, what's on the left side of the equation and what's on the right side of the equation. The probability of A or B is 6. Sorry, not probability, number. So the number of elements in A or B is 6. The number of elements in A was 3, plus the number of elements in B was 3. Those add up to the same. So these are mutually exclusive based on this. The probability of A or B was 6 out of 6, which is 1. The probability of A was 1/2. Probability of B was 1/2. That totals to 1. So again, both verify that it's mutually exclusive. All right, we're going to continue on with some more examples here. So the next one says to consider the experiment of rolling a die. Event A is going to be that there's an even number thrown. And event B is that a multiple of 3 is thrown. And if you remember multiples, a multiple means 3, 6, 9, 12, and so on. So that means the number's getting bigger. So 3, 6, 9, 12, and so on. In this case, we're looking at a die, so the highest that we can get up to is 6. So before I put them in a Venn diagram, I'm actually going to list the outcomes. So event A, the events for A is an even number is thrown. So that's going to be 2, 4, and 6. Sometimes it's easier to list your sample space first and then arrange it into the Venn diagram. Event B is a multiple of 3, so 3 and 6. A or B would be 2, 3, 4, and 6. Notice there's some numbers missing, which means there's going to be some numbers outside of the circles. And A and B will be 6. So if we arrange that into a Venn diagram, we've got the 2 and the 4, 6 is in the overlap, and then we have a 3 here. Now, 2, 3, 4, and 6 means that 1 and 5 have to be outside of the space. So this should still add up to our complete universal set, which is all 6 numbers on the die. Now, if we look at the number of elements in A, there's 3 elements in A. The number of elements in B is 2. The number of elements in A or B is 4. And the number of elements in A and B is 1. For the probabilities of A, there are 3 out of 6 for the event A, which is 1 out of 2. The probability of event B, there's 2 out of 6, which is 1/3. A or B is 4 out of 6, which is 2/3. And the probability of A and B is 1 out of 6. Now, this particular example has an overlap. And if there's an overlap, that means they're not mutually exclusive. So if there's an overlap, then they're not mutually exclusive. So you'll see me write it as not ME. Now, if we look at the Venn diagram again, because there's no overlap, that means these are not disjoint sets. So there was no overlap. Or sorry, this had an overlap. Sorry, my apologies. So there is an overlap. That means that they are not disjoint because there's that overlap there. All right, so again, just like before, we can verify this using left side, right side. So for the numbers of elements in A or B, we had 4 elements that were in A or B. The number of elements in A, was 3, plus the number of elements in B, which was 2, minus the number of elements that was in both was 4. So 3 plus 2 minus 1 is 4. So that verifies that these are not ME. We can again look at the probabilities, and so for our probabilities, the probability of A or B was 2/3. The probability of A was 1/2. The probability of B was 1/3, and the overlap was 1/6. So it's the probability of A plus the probability of B minus the overlap, and that gives us 2/3. So again, not ME. All right, let's take a look at example number 3 here. So it says, in each case, state whether the events A and B are mutually exclusive or not. So again, if they're mutually exclusive, that means there's no overlap. So if it's ME, ME means no overlap, or they're disjoint. All right. So the first example here, it says, the experiment is a die is rolled. Event A is an even number occurs, and event B is an odd number occurs. Well, we ask ourselves, is there any way that we can get an even odd? And we can't. So there's no overlap. So this is mutually exclusive. The next one, it says a card is drawn from a standard deck, a face card is selected, and a club is selected. Well, we can get a face card that is a club. So we can have a face card and club. That's possible. Okay, for example, we could have a king of clubs, we could have a queen of clubs, a jack of clubs, and so on. So these are possible. So this is not mutually exclusive. And the third experiment, it says 2 dice are thrown, the dice show both the same value, and the total score is 11. So we're asking ourselves, can we get doubles that total 11? And we can't. If we think about all of our doubles, we have 1s, 2s, 3s, 4s, and so on. The double 5s gives us a 10, the double 6s gives us 12. We cannot get an 11 with doubles. And so this is mutually exclusive because there's no overlap. All right, looking at Venn diagrams again, there's just a lot of examples today just so you can see all the varieties. Events have been represented on a Venn diagram. State all the pairs of events that are mutually exclusive. In other words, all the events that have no overlap. Well, A is mutually exclusive with everything. So A and B is mutually exclusive. A and C is mutually exclusive. A and D is mutually exclusive. And so that's off the table. Now, if we look here, C and D overlap, B and C overlap, but B and D do not. So B and D are also mutually exclusive. Quite commonly, especially when we had the diploma exam, questions are often asked. You're given information like you're going to see in example 5 here, and you're just asked, are they mutually exclusive or not? So quite often you're asked to use a formula to verify whether this is the case or not. So here it says, use the given information and the probability formula to determine whether events A and B are mutually exclusive. So literally this just means plug it into a formula and see if it's true. So if they're mutually exclusive, then that means the probability of A plus the probability of B has to equal the probability of A or B. Notice or means add. So while these are probability formulas, we can often use them to help us out when we're doing sets questions as well. So the probability of A is 1/4 plus the probability of B is 1/3. And if we add those up, that gives us 3/12 plus 4/12, which is 7/12. So this is mutually exclusive. All right, example number 6. A card is drawn from a standard deck of 52 cards. Using the formulas, determine the probability that a 9 of diamonds or a heart is drawn. Whenever we're doing probability questions, it's important that you list your probability outcomes. So the probability of a 9 of diamonds, so you can draw the diamond or just write a D, or a heart. So the probability of 9 of diamonds or a heart. Well, we ask ourselves, can we get a 9 of diamonds that is also a heart? The answer is no. So it's just going to be the probability of diamonds, a probability of 9 of diamonds, plus the probability of a heart. Okay. If this was not mutually exclusive, then we would subtract the overlap. So probability of 9 of diamonds, well, there's 1 9 of diamonds out of 52 cards. Probability of hearts, there are 13 hearts out of 52. So our probability is 14 out of 52, which reduces to 7 out of 26. So remember, we always want to write these as fractions in lowest terms, unless we're specifically asked for a decimal or a percent. All right, the next one says the probability of a 9 or a heart. So this is the probability of 9 or a heart. Well, in this case, this is not mutually exclusive because we can get a 9 of hearts. So the probability of a 9 plus the probability of a heart minus the probability of a 9 and a heart. So the probability of a 9 is 4 out of 52. There's 1 in each suit. Plus the probability of a heart is still 13 out of 52. And 9 of hearts, well, there's 1 9 of hearts. So minus 1 over 52 gives us 16 over 52. And that reduces to 4 over 13. All right, before we go into more examples here, I want to draw your attention to your formula sheet. So on your formula sheet, you will have this probability section, right? And we've already looked at factorials and permutations and combinations, but now I want to draw your attention to the 4 formulas near the bottom there. And we've already dealt with these first 2, and we're going to be looking at the next 2 in the next lesson. But it's important that you remember the order. You're given the formulas, but you're not given what each one represents. So it's important that you remember that. So the first one here is mutually exclusive. Notice there's no overlap. Okay, so mutually exclusive, there's no overlap. Not mutually exclusive. So this is where you're subtracting your overlap. So they're both A or B. So this here represents or. So for mutually exclusive or not mutually exclusive, we're looking at or scenarios, and we're looking at whether we have to subtract the overlap or not. The other 2 are the ones that we're going to get into in the next lesson. And so the first one is independent and dependent. And I won't go into details with those right now. But remember, mutually exclusive, not mutually exclusive, independent, and dependent. All right, so when we're talking about mutually exclusive events, that also brings up complementary events. And it's important for you to know that an event can be mutually exclusive, but not necessarily complementary. And we're going to go through some examples here shortly. So 2 events are described as complementary if they are the only 2 possible outcomes. For example, if I'm rolling a die and the outcome is either evens or odds, that would be an example of a complementary event. If we're doing some testing and it rains on a particular day, well, the solution is either it rains or it doesn't rain. Those are our only 2 outcomes. And so either one event happens or the other event happens, but not both. And there's no other possible outcomes. So if there are only those 2 outcomes and no others, and they're exact opposites of each other, then it's complementary. So next example here, it says, consider the rolling of a die to see whether the result is odd or even. So as I just said here, odds and evens are complementary, but let's look at why. So it says the events odd or even are complementary because the result must be either odd or even. It can't be both. And if I were to draw a Venn diagram, there would be nothing else outside of those boxes. So if I were to draw a Venn diagram here, there's no overlap. Odds would be 1, 3, 5. evens would be 2, 4, 6, and there's nothing lying outside those boxes. So no overlap, and everything is in those two circles. So when two events are complementary, we can use the following properties, and we've looked at these already before. The probability of A plus the probability of not A is 1. Okay, we also represented it this way. The probability of A plus the probability of A bar equals 1. So two different ways to represent the same thing. Or we can take 1 minus the probability of A to get the probability of not A. So the probability of A bar would be 1 minus the probability of A. And vice versa. We could take 1 minus the complement to get the original as well. So let's look at this example here. It says, consider the experiment of drawing a card from a standard deck. The following events are defined. So event A is a face card being selected, B is a red card, C is a club, D is an ace, and E is a black card. So the question is, which pairs of events are mutually exclusive? In other words, which ones have no overlap? Okay. You may want to pause the video and try some on your own, but I'm going to go through the answers here right away. All right, so the ones that are mutually exclusive. If we look at event A, a face card, well, we can have a red face card, so that's not it. We can have a face card that's a club, so that's not it. But we can't have a face card that's also an ace. So event A and D is mutually exclusive. We can't have a face card that's also an ace. And then A and E, well, we can have a black face card. So let's look at event B, a red card and a club. We cannot have a red card and a club, so B and C is mutually exclusive. We can have a red ace. We cannot have a red black card, so B and E is also mutually exclusive. So look, we can have an ace that's a clubs, we can have a black club, and we can have a black ace. So these are our three events, A and D, B and C, and B and E. Now the question is, which of these ones then is complementary? So complementary means that means that they're exactly the opposite. Well, A and D, we're looking at a face card and an ace. Well, a face card and an ace is one outcome, but we also have other outcomes outside of that Venn diagram if I were to draw it. B and C, a red card and a club. Well, red clubs aren't possible, but if I draw my Venn diagram, not everything's going to fit into those two circles. But for the last one, a red card and a black card, well, if I were to draw a Venn diagram of this, all of my red cards would be in one event, all my black cards would be in the other, and those are the only possible outcomes. Okay. Whereas if we were looking here at A and D, if we drew a circle with face cards and a circle with aces, face cards and aces, there would be a bunch of other cards out here. So 1s and 2s and 3s and so on. So this is not mutually exclusive or not complementary, whereas this one is complementary. So B and E is mutually exclusive and complementary. All right, another example here. So it says blocks of different shapes and colors are placed into a bag. There are 3 cubes, 1 blue, 1 red, and 1 green. There are 2 pyramids, 1 red and 1 yellow. And there are 5 cylinders, 1 blue, 1 yellow, 3 red. Now, this is sometimes almost like a trick question. Everything in here is talking about 1, 1, 1, 1, 1, and then all of a sudden they throw in a 3 at the end. So it's important when you're totaling these up that you don't miss that 3. So if we add these up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 shapes. So there are 10 shapes here. Very easy to look at that and only give yourself 8 shapes because, again, everything's been ones except for the last phrase. So the first question says, determine the probability that a block selected at random will be a pyramid or a cube. Well, we ask ourselves, is this mutually exclusive or not? And so you ask, can I have a pyramid cube? And the answer is no. We cannot have overlap, so this is mutually exclusive. So the probability of a pyramid or a cube is the probability of a pyramid plus the probability of a cube. It's important that you get in the habit of writing out these formulas. For one, it helps you to kind of frame the question, but secondly, it's also important that you know how to represent this as a formula. So the probability of a pyramid, there are 2 pyramids, so 2 out of 10. The probability of a cube, there are 3 cubes, so 3 out of 10. gives us 5 out of 10, or 1/2. Now, the probability that the shape we choose will not be red. Well, there are 3 reds here, and we've got 1 red here, and 1 red there. So 3, 4, 5. So that means, so if we have 5 that are red, 5 red, that means there are 5 that are not red. So the probability that it will not be red is 1 minus the probability that it will be red. So 1 minus 1/2, or 1 minus 5 over 10, equals 5 over 10, which equals 1/2. Now again, you can just count those up and say, well, there's 5 out of 10 that aren't red. Now the third example here, it says the probability that it will be red or a cylinder. So the probability that it'll be red or a cylinder. Well, it is possible to have a red cylinder, because if we look in the cylinders here, we have 3 red cylinders. So this is going to be the probability of red plus the probability of a cylinder minus the probability of red and cylinder. All right, so the probability of being red is 5 out of 10. The probability of being a cylinder is 5 out of 10. And the probability of being a red cylinder is 3 out of 10. So 5 plus 5 is 10, minus 3 is 7. So there's a 7 out of 10 chance of being red or a cylinder. And one last example. Gavin and Bennett are asked to solve the following problem. 200 people with neurology symptoms, which include headaches and backaches, participated in a study to evaluate a pain relief medicine. All the people took the medicine and the results were as follows. 60 people experienced headache relief, so 60 people had headache relief. 126 people had backache relief, and 36 people experienced relief from both. So the first question is, what is the probability that what is the probability that a person taking the drug experiences relief from at least one of the 2 symptoms? So they have relief from headache or backache, or both. So the probability of headache or backache. Neither of the 2 symptoms. So neither of the 2 symptoms means the probability of not headache relief and not backache relief. So let's take a look at some scenarios here. Gavin has decided to solve the problem using a probability formula. So he's going to be looking at the probability of H or B being the probability of H plus the probability of B minus the overlap. Now, we've already been told there's an overlap, so we know this is a not mutually exclusive event, so not ME. So he's figured out that the probability of headache is 60 out of 200, which is 0.3. The probability of backache relief was 126 out of 200, which was 0.63. And the probability of relief from both is 36 over 200, which is 0.18. So for part I, to find the probability of H or B, he's going to take that 0.3 plus the 0.63. So probability of H plus the probability of B minus the probability of both. So minus 0.18. And he gets a probability of 0.75. Now, if the probability of getting the relief from at least one is 0.75, then neither would be 1 minus the probability of H and B. I just realized that should have been not H or not B. We'll just change that. We'll just write the complement. So the probability here is going to be 1 minus 0.75. Because if there's a 75% chance or 0.75 probability that there will be relief, then the opposite of that is no relief. So 1 minus 0.75 would be 0.25. So 25% chance of no relief. Now, a lot of students actually find that Venn diagrams are even more helpful than the formulas. What I like about this is that because there's two ways to do the question, that means there's always a way to check your work, which is something I like. All right, so Bennett has decided to solve the problem using a Venn diagram. So we have 36 in the overlap. And for headache relief, we had 60 people experiencing headache relief. And so if you remember from sets, 60 minus 36 means that there are 24 people who are receiving headache relief but not backache relief. And then for backache, there's 126. Well, 126 take away 36 gives us 90. So there are 90 people that have backache relief but not, or sorry, they have backache relief but not headache relief. Now, that doesn't total up to everything, so we need to add these up. These add up to 150, and since there were 200 patients surveyed, that means there's a 50 outside, so this has to all add up to 200. So for the first one to see, the question is how many people experience at least one symptom relief? Well, that's going to be our circles here, H or B. And so that's 24 plus 36 plus 90 out of 200, which is 150 out of 200. And in lowest terms, that's 0.75. Now for part 2, we have no relief. So that's 50 out of 200 people that had no relief from their symptoms, which is 0.25. All right, so that's our lesson. Hopefully I've given you lots of examples. Remember that when we're talking about mutually exclusive and not mutually exclusive, we're looking at or, and we're asking ourselves, is there an overlap or not? All right, that's it for today, guys. Have a great day, and we'll see you soon.